Okay, so the second talk is given by Francesco Parolini on sound abstract non-exploitability analysis.
Okay, thank you. So I'm Francesco Parolini, and this is a work that I did with my supervisor, Antoine Minet. And this talk is going to be about the AI part of VMKI, because it's about abstract interpretation. So abstract interpretation is this technique to prove the absence of runtime errors. And one of the first things that you learn about this is that it's usually sound but not complete, meaning that you can have false positives in the output of your analyzer. And if there are too many false positives, what happens is that the analysis could be meaningless because there is too much noise and you cannot identify the true errors in your programs. And so what usually happens is that to lower the number of false positives, we use more precise and usually costly abstract domains. And sometimes what happens is that if you use precise enough abstract domains, you can even remove all the alarms. So if you do not have any alarm in the output of your abstract interpreter, then you proved that a piece of software is correct. But this is possible. Oftentimes, what we find is something more like what you see on the right part of the slide. That is, you have false positives, and in general, there is no way to arrive to zero for any program. So false positives do matter, and we would like to lower them. And our work starts from this assumption, that is that not all bugs are equal. So if you consider the program on the left, it's a C program that has a use input function that takes as input an array of characters and then copies its contents to an array of 10 characters. And what can happen is that if the input array is longer than 10 characters, we have a buffer overflow. So we have a runtime error. And indeed, since from main we call it with a buffer of 100 characters, this program is not safe. But what if we consider the program on the right? So it's the same program. The only difference is that you read the content of the input buffer from user input. And so this program, intuitively, it's more dangerous because it's an external user of the application that can decide whether there is a runtime error or not. So it becomes a matter of security. And so our key observation is that the security-related bugs are more dangerous. And this work, it's about lowering the number of false positives and, in general, alarms by reporting only the security-related warnings. And we develop a framework based on abstract interpretation that uses a novel hyperproperty called non-exploitability, which we then use to put forward this sound static analysis that we implement and run on some programs. So starting from the definition of non-exploitability, we consider the classic while language. The only difference with the traditional one is that we have input and random statements. So input is reads from the user a number that is considered to be dangerous, while random reads a random number that is not considered to be dangerous. For the semantics of our system, we have variables and memories, where memories are, as usual, functions from variables to integers. What it's maybe a bit different is that our program states are not simply memories, but they are triplets. For the first component, indeed, it's the memory. But then we also have the unbounded sequence of input numbers that are inserted by the user and the unbounded sequence of random numbers that it's read from random statements. And why do we do this? That's because then we can have this semantics, which is a deterministic semantics. So it's a function from states to states. So we do support non-deterministic statements by embedding the non-determinism inside of the states. And what's a bit different from usual is that we explicitly represent states in which an error occurred as states in which we have this variable return that is set to 1. And return is a meta variable that you cannot read or write from programs, but we use to represent the fact that there was an error or not. So it's a meta variable. So we can go to the definition of non-exploitability. And the intuition is that the user should not be able to interfere with the correctness of the program. What this means in our setting is that by changing only the user input at the beginning of the program, we should not observe any change in the return variable, that is the variable that talks about the correctness of the program. So this is the formal definition. So non-exploitability is a set of semantics, so it's an hyperproperty. And the idea is that if we consider every pair of executions inside of our semantics, if we start from the same memory, so at the beginning of the program we have the same setting for program variables, we change the user input, so the user inserts a different sequence of input numbers, and we consider the same sequence of random numbers at the beginning of the program, then this must imply that at the end of the program, the value of the return variable must be the same. And this formalizes the idea that the user, by changing only user input, we cannot interfere on whether there is a runtime error or not.
It looks like a non-dependency.
Yes, indeed. It's a kind of non-dependency. Yeah. And this makes it possible to differentiate these two programs. So the one on the left, it's indeed exploitable. That's because if we read from user input 0, and then we perform 1 over x, we have a runtime error. So in one execution there is an error. And if we read from user input 1, then there we have no runtime error. So the user can trigger whether there is a bug or not. On the other hand, the other one is non-exploitable, because if we read any number from random, and then we perform 1 over that number, even though there might be a division by 0 here, the user cannot decide whether this is triggered or not. So that's a semantic difference between the two. But then how do we prove it? So I won't tell you the details, but the idea is that we start from a semantic definition of taint. The idea of taint is that a variable is tainted if and only if the user can control its value. And I want to stress that it's not a syntactic definition that we have in the paper, but it's a semantic definition of taint. And one of the results that we have is that a program is non-exploitable if and only if return is not tainted in its semantics. Where this tainted, it's a semantic definition of taint, so we cannot compute it. But even though this theorem doesn't give us an algorithm to compute how to prove non-exploitability, it gives us the idea that we might be able to use techniques to perform a taint analysis and track whether this return variable is tainted or not. But it's a bit different from traditional taint analysis, because usually in taint analysis you have parts of the code that are syntactically known where you don't want user data to flow in. For instance, when you call a database or you do something of that kind. But here, no, it's not the case, because we do not know where the expressions that can be dangerous. Why? Because the expressions that can be dangerous are those with runtime errors. So, is this a division by 0? The answer is that it depends. Because if x is 1 and y is 2, we don't care whether the user can put some value here because there is no division by 0. But on the other hand, if x equals y, yes, there is a division by 0, and we don't want the user to be able to trigger a path that makes this, reaches this program point. And what I'm really trying to say here is that it's important to track the values of the variables to perform this analysis. It's very essential. And without the details, what we do in the paper is that we combine existing well-known abstract domains for traditional abstract interpretation with this taint analysis. And what we obtain is a strictly more precise taint analysis. And here I have a small example. So it's a program where initially we set x to y to 1. And while x is less than 20,000, if the user inserts 1, then we multiply x by 468. Otherwise, we multiply x by 1053. So what our analysis infers is that at the end of the loop, x is at least partially user controlled, because the user can somehow decide whether what is its value up to a certain level. But then what we do is we perform this. So if x modulo 117 is not 0, we perform a division by 0. So what this looks like, it's a program where depending on user input, there might be a division by 0 because x is user controlled. And without knowing the values that we have, this would be the case. But actually, this program point it's unreachable. We cannot reach this program point ever, and we can see this with traditional congruence analysis. And so what we can do with our technique is proving indeed that this program is non-exploitable. But in general, it's quite difficult, impossible without the values of the variables here. So since it's a very applied problem, we have experimental evaluation. And the implementation is written in OCaml, and it analyzes C. It's a small implementation of 10,000 lines of code. And what we find is common safety exploitable errors. So index out of bounds, null pointer dereference, those kind of things. And we implemented it for the MOPS analyzer that is a C and Python analyzer that we have at my lab. We considered 77 real-world programs from CoreUtils. It's a collection of command line utils up to 4,000 lines of code, to which we added the 13,000 test cases from Juliet. And what we did is we compared the normal analyzer in terms of performance and precision. So these are the results. We can consider only CoreUtils because it's more meaningful. So for the normal analyzer, that is MOPSA, we found 4,715 alarms in 1 hour and 70 minutes. While for the modified non-exploitability analyzer, we found 1,217 alarms in 1 hour and 28 minutes. And if we do the math, these results improving, and I actually mean proving, that more than 70% of the alarms are non-exploitable. So we can filter out 70% of the alarms because they cannot be triggered by an external user according to our definition of non-exploitability, of course. And the runtime performance overhead is under 16%. So just to conclude, false positives are challenging in abstract interpretation, and we want to keep them low. And if we assume that security alarms are more dangerous, which is often the case, to reduce the number of false positives, we can report only those. And with a quite short implementation of only 10,000 lines of code, a low performance overhead of up to 16%, this gives really good real-world results on software that is non-trivial, up to 4,000 lines of C code. Thank you very much.
Questions?
So you said that usually to avoid false positives, you increase the precision. So I'm wondering, how does this correlate with the 70%? So if you increase the precision, does it still remain 70% of?
Yeah, we compared different analyses, and no, it goes lower the performance overhead when we go from intervals to polyhedra, for instance.
Not the performance overhead, but the percentage of the exploited.
Oh yeah, yes, indeed. It's more precise also the taint analysis, because there might be cases in which a relational analysis can prove that a variable is not tainted. So yes.
So you get more than 70% when the precision increases?
Yes, indeed. Also, because you can sometimes you just not remove the taint, but also because you prune paths that are not executed ever.
I was just wondering whether you could, if you assume that there is no random choice, or if you reinterpret it, could you use this to also prove that programs are deterministic, so that you and will maybe generate a test case when there is an error that would be triggered by essentially arbitrary execution? Because if user cannot control the behavior, and if all the other sources were actually just approximations of multiplication or something else, then in principle the program should be deterministic, no?
Yeah, I think it's possible. I have to think about this. I'm not sure.
Quite a while ago, Xavier Rival proposed a notion of semantic slicing, which would slice back from a property and then see a kind of cone of influence for that. And it seems to me that you could slice back from undefined behaviors and see if the cone of influence contains external inputs. Have you compared with that approach, or?
We did not compare, but it's definitely related. Slicing and also abstract slicing is definitely related to this. Absolutely. What we do is just somehow we start from the beginning of the program, so it's a whole program analysis and it's a forward analysis that flows through all the reachable program points, while slicing somehow goes back. But yes.
Anybody else? I have one question. So what about termination? Is it termination sensitive? What happens if let's say the user can trigger non-termination in some way? Is it? Yeah.
So this analysis is thought to deal with safety problems, so division by zero and stuff like that, and it's non-termination insensitive. So if we don't care about non-termination. We would need a different technique for the analysis to prove that a user can trigger non-termination.
But you don't care about the non-termination, but then your program may not, the user may make your program non-terminate, and then you don't have a return.
No. Yeah.
And then you do have a difference in the behavior of the program.
Yes. So let me go back to.
So then.
Yeah. If one doesn't terminate, you wouldn't find the.
Yeah. So then you do care of whether a program terminates or not. Because then you have a difference.
Yes, I guess. I'm not sure. That's it.
Approximation.
Yeah.
I think it's correct.
Okay.
Then I have one. It's also related to responsibility analysis, because if you prove that the input is responsible for a tainting, then it's a bit more precise and more expansive also.
Yes, indeed. It's we started from the dependency analysis. So yes.
And responsibility.
Responsibility analysis. Oh yes. Okay. Yes.
In between. You are in between.
Yes, indeed. Yeah.
So I have a follow-up to Victor's question on the determinism. If you have a concurrent program, then the scheduler is almost like a random input, right?
Yes. Yeah, I think so.
Can you try this on concurrent programs? You could.
We didn't try, but I think it's possible, yes, indeed. And it would be interesting, actually.
Okay, let's thank the
Alright.
speaker.
Okay.